Welcome to a place where curiosity can slow down and science moves softly, guiding you toward rest. Tonight, we're exploring one of the most sudden and dramatic cold reversals in Earth's long history. Picture the planet emerging from a deep ice age. Massive glaciers are shrinking, frozen rivers begin to flow again, and life cautiously returns to valleys and open plains. Green slowly replaces white, forests spread, animals roam farther, and humans begin to sense a gentler world ahead. Then, almost without warning, everything changes. The warmth stumbles, the cold surges back. In what feels like the blink of an eye, winter tightens its grip once more, holding Earth in an icy pause for over 1,000 years. Scientists call this event the Younger Dryas. You might think of it as the moment when spring was interrupted and winter returned with force. This is a story shaped by shifting climates, human struggle, and unanswered questions. A world ready for change, only to be pulled back into the cold. Before we continue, take a moment to notice where you are. What does the air outside feel like right now? Is it warm, rainy, cool, or already touched by winter? That small detail connects your present moment to this ancient story of Earth's constant climate dance. And if this slow journey through science helps you relax or drift toward sleep, a gentle like or subscribe helps this quiet space reach others who might need it too. No pressure, just something to keep in mind. Now, let's ease into the past. More than 12,000 years ago, the world stood at a turning point. The vast ice sheets of the last glacial maximum were retreating after dominating the planet. For tens of thousands of years, ice covered much of North America, Northern Europe, and large parts of Asia. Glaciers stretched for miles, burying mountains and carving valleys deep into the land. Around 14,000 years ago, temperatures began to rise, ice melted, enormous lakes formed, rivers surged with fresh meltwater, and ecosystems shifted. Mammoths, giant bison, and other massive animals still walked the land, sharing a shrinking frozen world with humans who were learning to hunt more efficiently, gather plants, and experiment with early forms of settlement. For a time, the future seemed clear. Forests expanded, grasslands grew richer, and humans found more opportunities to stay in one place, rather than endlessly follow migrating herds. But instead of continuing toward a stable, warm climate, the planet reversed course. Temperatures dropped sharply, glaciers stopped retreating, and, in many regions, began advancing again. This sudden plunge into cold conditions became known as the Younger Dryas, named after a small Arctic flower Dryas octopetala whose pollen appeared in ancient sediments, marking the return of frigid ecosystems. What makes this period so remarkable is its speed. Within just a few decades, global temperatures fell dramatically, winters grew longer, summers weakened, crops struggled, herds thinned, and human communities were forced to rethink how they survived. And yet, they endured. They adapted, moved, and learned. Without that resilience, human history might have taken a very different path. Scientists continue to debate what caused this sudden freeze. Ice cores from Greenland preserve year-by-year climate records, clearly showing a sharp temperature drop, a millennium of cold, and an equally rapid return to warmth. Lake sediments, fossils, and layers of ancient charcoal suggest widespread fires and environmental stress. Some researchers believe massive floods of glacial meltwater disrupted ocean currents, cutting off the flow of warmth to the north. Others point to volcanic activity, or even the possible impact of a comet. Whatever the cause, the result was unmistakable. Earth's climate shifted back toward ice age conditions with astonishing speed. For the people living through it, this wasn't data on a graph. It was biting wind, failed harvests, and difficult hunts in the Near East. Early farming communities like the Natafians had begun settling and harvesting wild grains. The Younger Dryas challenged them, possibly pushing humans closer to organized agriculture as wild resources became unreliable elsewhere. Hunter-gatherers followed changing animal migrations, or moved into regions less affected by the cold. These decisions shaped the paths along which future civilizations would later rise. As the cold endured, ecosystems transformed. Many large animals that had thrived during the warming phase began to disappear. Human hunting played a role, but the harsh climate added immense pressure. Mammoths and saber-toothed cats struggled, while smaller, more adaptable species survived and filled the gaps they left behind. When the Younger Dryas finally ended around 11,500 years ago, warming returned. Just as abruptly, glaciers melted again, temperatures climbed, and the Holocene epoch began. The stable, warm period that continues today for humanity. This shift opened the door to farming, permanent settlements, and the foundations of civilization itself. In that sense, the Younger Dryas, despite its harshness, helped shape the modern world. Tonight, we'll move slowly through this story. We'll explore the world before the cold returned, the theories behind the sudden freeze, and how it reshaped both nature and humanity. It's a tale of fragile balance, rapid change, and survival against the odds, a reminder that Earth's climate has always been capable of surprising turns, and it all begins with a warming world, melting ice, returning life, and a winter that came back when no one expected it. In the Near East, the Natafian communities encountered one of the most defining trials in human history. Even before the onset of the Younger Dryas, they had already begun constructing stone dwellings, storing surplus food, and forming larger, more permanent settlements. Their way of life was becoming increasingly stable, supported by wild grains that flourished as the climate warmed. But when colder conditions suddenly returned, this balance was disrupted. Harvests became unpredictable, and some settlements were left behind altogether. Others, however, chose a different path. Rather than abandoning their way of life, they intensified their efforts to manage plant growth. Certain groups began carefully nurturing wild cereals, a process that gradually led to the domestication of crops such as wheat and barley. In this sense, the harsh climate of the Younger Dryas may have accelerated humanity's shift toward agriculture. Without this abrupt cooling, farming might have taken many more centuries to develop. Across North America, human societies were also reshaped by these climatic changes. The Clovis culture, recognized by its distinctive stone spear points and its reliance on hunting large animals, appears to vanish from the archaeological record during the Younger Dryas. This disappearance coincides with the extinction of mammoths and mastodons. As temperatures dropped and megafauna declined, human groups were forced to adapt. They shifted their focus toward smaller animals, fishing, and plant-based foods, developing new tools and survival strategies suited to the changing environment. The sudden end of the Clovis culture remains one of the great mysteries of this era, but climate change clearly played a central role. Food shortages were only part of the challenge. Cooling temperatures also transformed water systems. In Africa, lakes shrank, rivers altered their courses, and once productive landscapes became dry and inhospitable. Human populations began clustering around dependable water sources such as the Nile, reshaping settlement patterns that would influence history for thousands of years. In Asia, weakened monsoon systems brought drier conditions across vast regions, forcing migrations and new adaptations for the people living through it. These changes were not abstract trends, they were felt in failed harvests, empty wells, and long journeys in search of drinkable water. Cold, scarcity, and uncertainty also left a mark on human culture. Periods of stress often drive innovation, and the Younger Dryas was no exception. People refined their tools, strengthened their shelters, and developed better methods for storing food. Clothing became more suitable for colder climates, and homes were built to withstand harsher conditions. Yet even in these difficult times, art and ritual persisted. Figurines, carvings, and cave paintings suggest that humans continued to seek meaning, beauty, and connection. Survival was never only about food and shelter, it was also about community and shared identity. The Younger Dryas may also echo in ancient oral traditions. Many cultures preserve stories of extreme cold, sudden floods, or dramatic environmental upheavals. While direct links are impossible to prove, it is tempting to see these myths as distant memories of a world turned upside down, tales of endless winters, vanished animals, and lost worlds passed down through countless generations. The impact of this freeze was so profound that its influence may still linger in human storytelling today. One striking aspect of the Younger Dryas is how uneven its effects were. Not all regions experienced the same intensity of cold. Some areas became drier rather than colder, while others faced both challenges at once. This climatic instability created both danger and opportunity. Some human groups declined, while others adapted and even thrived. The ability to move, share knowledge, and innovate often determined whether a society collapsed or endured. This period also shaped the future of domesticated plants and animals. As people experimented with controlling food sources, certain species proved more suitable for harsh conditions. Goats and sheep, resilient animals capable of surviving on sparse vegetation, became increasingly important in the Near East. Dogs, already valuable hunting companions, became even more essential, helping humans track and capture prey. Hardy plants able to withstand cold and unpredictable weather were among the first to be cultivated. These early choices, made under pressure, laid the groundwork for agriculture and animal domestication that would define life in the Holocene. The Younger Dryas highlighted how deeply humans were connected to their environment. Every shift in vegetation, every change in animal populations, and every alteration in rainfall patterns rippled through human societies. This period was a powerful reminder that humans were not separate from nature, but part of it, subject to the same forces and cycles. Survival depended on understanding those forces, adapting to them, and in some cases, attempting to shape them through early farming practices. As the Younger Dryas continued, entire generations grew up knowing no other conditions, cold and scarcity, were not temporary crises, they were normal life. People were born, raised families, and died within this long freeze, never knowing that warmth would eventually return. It was a winter lasting over 1,000 years, long enough to reshape ecosystems, cultures, and the course of history itself. Yet even during this prolonged cold, life persisted. Plants found ways to survive, animals adjusted their ranges, and humans continued to innovate and endure. When warmer conditions finally returned, it was these survivors, human and otherwise, who shaped the next chapter of Earth's story. During those centuries of cold, resilience ruled the world. When scientists later uncovered evidence of the Younger Dryas through ice cores, pollen samples, and ancient sediments, a pressing question emerged. How could the Earth, after more than a millennium of warming, suddenly plunge back into near ice age conditions? And how could it remain there for so long before shifting again just as abruptly into the stable climate of the Holocene? This mystery has fascinated researchers for decades, not only because of what it reveals about the past, but because it demonstrates how sensitive Earth's climate system truly is. The most widely discussed explanation centers on the oceans. Earth's climate is shaped not only by the atmosphere, but by vast ocean currents that transport heat around the globe. This system, known as thermohaline circulation, is driven by differences in temperature and salinity. Warm, salty water flows northward along the surface of the Atlantic, cools at higher latitudes, becomes denser, and sinks, flowing back southward in the deep ocean. This process carries enormous amounts of heat, keeping regions like northern Europe far warmer than they would otherwise be. As ice sheets melted at the end of the last ice age, massive quantities of fresh water poured into the oceans. In North America, enormous glacial lakes, especially Lake Agassiz, held staggering volumes of water. When ice dams containing these lakes failed, fresh water rushed into the North Atlantic, diluting its salinity. This may have disrupted the sinking of dense water, weakening or even halting the oceanic conveyor belt. Without this heat transport, the northern hemisphere cooled rapidly. Evidence supporting this theory comes from ice cores, ocean sediments, and microscopic marine organisms that reveal abrupt changes in temperature and salinity. Together, these records point to a sudden disruption of Atlantic circulation at the onset of the Younger Dryas. Still, not all scientists are fully convinced. Some argue that the timing and scale of freshwater floods do not perfectly align, leading to alternative theories involving volcanic eruptions or even a cosmic impact. One controversial hypothesis suggests that a comet or asteroid exploded over North America, triggering widespread fires and atmospheric disruption. While debated and unproven, this idea highlights how fragile the climate system can be. It is also possible that no single cause was responsible, that a combination of meltwater floods, volcanic activity, and other stresses pushed the climate past a tipping point. What is clear is that the Younger Dryas was not a simple, uniform global freeze. Some regions cooled dramatically, while others warmed or experienced shifting rainfall patterns. For the people living through it, the cause mattered less than the reality, a world that had suddenly become colder, harsher, and less predictable. Today, the Younger Dryas serves as a powerful warning. It shows that Earth's climate can change, suddenly, not always gradually. As modern scientists study this ancient event, they also look to the present, where similar systems such as Atlantic circulation are once again under stress. The mystery of the Younger Dryas may not be fully solved, but its lesson is clear. Earth's climate is dynamic, sensitive, and capable of rapid transformation. It reveals how something that appears relatively small, freshwater entering the oceans, can cascade through the entire climate system, reshaping the planet for more than 1,000 years. For the people living during that era, The great ocean conveyor was unseen and unknown. They had no understanding of salinity density or deep-sea currents. What they felt instead were the consequences. Summers growing shorter, winters becoming harsher, rainfall turning unreliable, and tundra spreading into areas once covered by forests. With modern science, however, we can now see that their struggles may have begun far away, with the subtle weakening of an ocean current thousands of miles from where they lived. What makes the conveyor belt explanation so powerful is not only its ability to account for the Younger Dryas, but its relevance today. Modern climate studies show that the Atlantic circulation is weakening once again, this time due to fresh water released by melting Greenland ice and increased rainfall driven by global warming. A complete shutdown like the one suspected during the Younger Dryas is unlikely in the near future, but even a slowdown could bring serious consequences: colder European winters, disrupted monsoons in Africa and Asia, stronger tropical storms, and damage to marine ecosystems. The same system that shaped the ancient freeze is still operating today, reminding us that climate is not static, but constantly in motion. The ocean conveyor also highlights how deeply interconnected Earth's systems are. Ice on land influences the oceans. Oceans shape the atmosphere. The atmosphere controls rainfall. Rainfall determines plant and animal life, and plants and animals, in turn, shape human societies. A single disturbance can trigger a chain reaction. The Younger Dryas was not caused by one isolated factor, but by a cascade of changes. With the ocean conveyor acting as the central link, scientists continue to debate the details. Did the fresh water come mainly from lake gases or from multiple meltwater sources? Was the release sudden or spread over centuries? Did the circulation stop entirely, or did it simply weaken dramatically? These questions matter for reconstructing the precise mechanics of the event, but the broader lesson is clear. The ocean conveyor is both immensely powerful and surprisingly fragile, strong enough to regulate climate across much of the planet, yet vulnerable to disruption by massive influxes of fresh water. This fragility is what makes the Younger Dryas such a striking warning. Climate change is often imagined as a slow process unfolding over millennia, yet the conveyor belt shows that climate can shift abruptly, within decades, with effects that last for centuries. The story of the Younger Dryas is therefore not only about the past, it is also about what the future might hold for those who lived through it. The faltering of the conveyor meant that a period of warming they thought secure suddenly slipped away. For us today, it serves as a reminder that this same system still operates beneath the ocean's surface, quietly transporting heat around the globe. If it weakens too much again, the consequences could be profound. The Younger Dryas gives us a glimpse of what that world might look like, a planet transformed not over ages, but within a single human lifetime. The great ocean conveyor, usually steady and unnoticed, may have been the unseen force that plunged Earth back into icy conditions. It was likely not the only factor, but it may have been the mechanism through which other forces, glacial floods, melting ice, or even cosmic events, were able to reshape the entire planet. If the Younger Dryas was triggered by ocean disruption, then meltwater floods from retreating glaciers were the most likely cause. These were not ordinary floods, but events of almost unimaginable scale. At the end of the last ice age, vast lakes formed along the edges of shrinking ice sheets, held back by walls of ice or ridges of debris left behind by glaciers. These lakes were silent reservoirs, storing volumes of water comparable to inland seas. When their natural dams failed, the release was sudden and catastrophic. Torrents of water tore across landscapes, reshaping continents and pouring immense amounts of fresh water into the oceans, with consequences felt worldwide. Among the largest of these lakes was Lake Agassiz, which formed in central North America as the Laurentide ice sheet retreated. At its peak, it covered an area larger than all 5 modern Great Lakes combined, spanning regions that are now Manitoba, Ontario, Minnesota, and North Dakota. For thousands of years, Lake Agassiz grew as meltwater streamed into it from the collapsing ice sheet, but its stability was deceptive. The ice dams restraining it were inherently weak, and eventually they failed. When the lake drained, it did so violently. Some estimates suggest that a single outburst released enough water to raise global sea levels by several meters. Rivers swelled to unprecedented sizes, valleys were scoured clean, and boulders as large as houses were carried downstream. Similar events occurred elsewhere. In the Pacific Northwest, repeated floods from ice-dammed lakes left behind landscapes, still visible today, giant ripple marks, deep scablands, and flood-carved channels. These were not minor regional disasters. They were continent-altering forces, rewriting geography in days or weeks. When such floods reached the oceans, they delivered enormous pulses of fresh water. In the North Atlantic, where dense, salty water normally sank to drive the conveyor belt, this influx acted like a barrier. Surface waters became fresher and lighter, preventing them from sinking. As circulation slowed, less heat was carried northward, and the climate shifted rapidly. Gradual warming abruptly reversed into glacial conditions. Evidence of these floods remains etched into the land. Ancient shorelines lie high above modern terrain. Vast channels stretch for hundreds of miles. Sediment layers reveal sudden surges of water, and massive erratic boulders mark paths carved by unstoppable currents. Geologists see a pattern of repeated outbursts, each capable of causing not only local devastation, but global disruption. The timing of one major outflow aligns closely with the onset of the Younger Dryas, round 12,800 years ago. Whether it was a single colossal flood or a series of massive releases, the effect was the same. The conveyor belt weakened, and the climate plunged into cold. For people living at the time, these floods would have been terrifying. Entire landscapes could vanish within days. Valleys rich in plants and animals might be stripped bare. Rivers once relied upon for food and water could become raging barriers impossible to cross. Communities near these lakes or their outflow channels may have been forced to flee with little warning, abandoning everything as the waters surged. It is easy to imagine how memories of such events became the roots of flood myths passed down through generations. Stories of deluges, angry waters, and worlds destroyed and reborn. Beyond immediate destruction, the floods reshaped the long-term environment. Rivers changed course. New lakes formed, sediments enriched some lands while burying others, and coastlines shifted as sea levels rose. The world became unstable, generation after generation. These floods also reshaped ecosystems indirectly by triggering the Younger Dryas itself. The return of cold altered vegetation zones, changed animal migrations, and forced humans to adapt yet again. In this sense, the floods were not merely local catastrophes, they were global agents of change, setting off a chain reaction that froze the planet for more than 1,000 years. The scale of these events is difficult to comprehend. Imagine a wall of water tens of meters high racing across open land, carrying icebergs, trees, and massive boulders, the ground shaking, the roar of water, the air filled with mist and debris. For survivors, such memories would have been unforgettable, carved deeply into cultural memory. It is no coincidence that flood stories appear in mythologies around the world. The effects extended far beyond cooling the north. Rainfall patterns shifted globally. In Africa, weakened monsoons turned one-screened landscapes back into desert. In Asia, disrupted monsoons altered rivers and limited agricultural potential. In parts of South America, rainfall increased instead. The result was a patchwork of hardship and opportunity across the globe. Today, scientists study these ancient floods not only to understand the Younger Dryas, but to anticipate what may lie ahead. As Greenland's ice sheet melts, it releases fresh water into the North Atlantic. Though far smaller in scale than Lake Agassiz, this steady flow is measurable and concerning. If it grows large enough, it could weaken modern ocean circulation, echoing the disruptions of the past. What makes this story even more striking is the speed of change. Earth's systems do not always shift slowly. They can lurch abruptly, driven by sudden events like glacial lake outbursts. One moment, forests expand and temperatures rise. The next, cold returns and landscapes are transformed almost overnight. For ancient humans, these were not scientific theories, but lived realities shaping every choice about survival. And so, the meltwater floods born from the dying ice giants carried more than water. They carried the power to reshape continents, disrupt oceans, trigger climatic reversals, and force humanity into new ways of life. They were the hidden force behind one of the greatest climate reversals in Earth's history. Among all explanations for the Younger Dryas, none has sparked more fascination and controversy than the idea that its trigger came not from Earth but from space. The impact hypothesis suggests that around 12,800 years ago, a fragment of a comet or asteroid entered Earth's atmosphere over North America, exploded in midair, and set off a cascade of environmental upheaval. It sounds like myth. Fire from the sky, sudden destruction, and a world thrown into chaos. Yet some scientists argue that the evidence points in this direction. Across dozens of sites in North America, Europe, and the Middle East. Researchers have identified a thin soil layer, marking the onset of the Younger Dryas. Within it are microscopic clues, melted rock particles, high-temperature minerals, carbon fragments from intense fires, and unusually high levels of platinum, a metal often linked to extraterrestrial material. Supporters believe these signs point to a massive airburst, similar to the Tunguska explosion of 1908, but far more powerful. Such an event could have ignited widespread fires, filled the atmosphere with dust and soot, and destabilized already melting ice sheets. The resulting fires alone would have been devastating, while smoke and debris could have blocked sunlight, rapidly cooling the planet. This hypothesis also aligns with the timing of megafaunal extinctions and the disappearance of the Clovis culture. In North America, proponents argue that a single catastrophic event could explain sudden ecological collapse, human disruption, and abrupt climate change. Some even suggest that ancient stories of fire from the sky and world-ending floods preserve echoes of this event. Critics, however, remain unconvinced. They argue that the materials found in the boundary layer can be explained by volcanic activity or wildfires, and that no definitive impact crater has been found. Without such evidence, they say, the case remains unproven. Supporters counter that an airburst would leave no crater, but skeptics argue that an event powerful enough to trigger the Younger Dryas should have left clearer traces. The debate continues, with new studies both supporting and challenging the hypothesis. Regardless of its ultimate verdict, the impact idea underscores a sobering reality. Earth's climate system is vulnerable to sudden shocks. History shows that cosmic impacts can radically alter life on Earth. Even if the Younger Dryas impact was smaller than the one that ended the age of dinosaurs, it could still have been powerful enough to tip an already fragile climate into chaos. For humans living at the time, such an event would have been incomprehensible: a blazing object in the sky, followed by fire, smoke, and a transformed world. Whether or not this scenario occurred, it captures the suddenness and severity of the Younger Dryas. Warmth vanished, stability collapsed, humanity adapted once again. Today, the comet hypothesis remains unresolved, neither fully accepted nor dismissed. But the Younger Dryas itself is undeniable. It happened suddenly, reshaped ecosystems, extinguished species, and tested human survival. Whether triggered by floods, volcanoes, or a visitor from space, the lesson remains the same: Earth's climate can change abruptly, and the line between stability and catastrophe is thinner than we often imagine. These were not simple, routine wildfires. They were immense events, so powerful that they etched themselves into Earth's geological memory marks that scientists can still recognize thousands of years later. The evidence is clear and widespread. In North America, sediment layers preserved in lakes and rivers reveal sharp increases in charcoal dating to roughly 12,800 years ago. Comparable signals appear across Europe and the Middle East. Even in Greenland, ice cores contain microscopic soot particles that could only have arrived after traveling thousands of kilometers on high-altitude winds. Together, these clues point toward fires on a continental, perhaps even global, scale. For researchers, the debate is no longer about whether fires occurred, but about why they were so intense and so widespread at this particular moment in time. One possible explanation is linked to the comet hypothesis. If a cosmic object exploded in Earth's atmosphere, the resulting shockwaves, heat, and debris could have ignited forests across vast regions. Supporters of this idea argue that the carbon-rich layers found at the Younger Dryas boundary represent enormous firestorms triggered by such an event. In their scenario, entire landscapes burned at once, animals were trapped, and human populations were forced to flee. The soot preserved in ice cores would then reflect smoke injected high into the atmosphere, dimming sunlight across the globe. Yet even without a comet impact, fire fits naturally into a climate already under extreme stress. Before the Younger Dryas, warming temperatures allowed forests to expand into areas once dominated by tundra. More trees meant more fuel. A sudden shift toward drier conditions, or abrupt climate instability, could have transformed these expanding forests into vast tinderboxes. Once ignited, they would have burned far more extensively than the smaller grassland fires typical of colder periods. In this view, fire did not cause the return of cold, but accompanied it. As ecosystems rapidly destabilized, volcanic activity may also have played a role. Eruptions can ignite fires directly and inject ash into the atmosphere, where it mixes with soot from other sources. Around the time of the Younger Dryas, evidence points to eruptions in multiple regions. None appear large enough on their own to explain the global signals, but combined with other stresses, they may have contributed to the widespread presence of fire and ash, whatever the trigger. The consequences of such firestorms would have been devastating. Smoke-filled skies would have reduced sunlight, lowering temperatures locally. Ash would have smothered soils and clogged rivers. Many animals would have been displaced or killed outright. For human communities, fire could destroy settlements, food supplies, and hunting territories in moments. To witness such events would have been terrifying. Flames racing across landscapes, air thick with smoke, and ground left black and lifeless. The ecological impacts would have lasted long after the flames faded. In many burned regions, soils may have been sterilized, slowing the return of vegetation. When plant life eventually recovered, it often favored different species better suited to the altered conditions. Forest-dependent animals declined or vanished, while species adapted to open landscapes expanded. Fire reshaped ecosystems just as profoundly as ice and flood. For humans, the aftermath was a double challenge. They had to survive the immediate destruction and then endure landscapes stripped of resources. Yet fire also created opportunities. Burned areas encouraged new grasses, attracting grazing animals. Charred ground made it easier for certain seeds to sprout. Some groups may even have begun using fire deliberately to shape their surroundings, an early step toward actively managing landscapes rather than merely surviving them culturally. These events likely left deep impressions. Survivors would have shared stories of forests disappearing in smoke, of flames falling from the sky, of animals fleeing in panic, passed down through generations. Such memories may have evolved into myths of destruction and renewal, tales of worlds burned and remade. Fire was only part of the story. With forests gone, exposed soils became vulnerable to wind. Dust storms would have lifted fine particles into the air, spreading them across vast distances. Wind-blown silt layers found in many regions may trace part of their origin to this unstable period. Combined with colder temperatures and shifting rainfall, dust added another layer of hardship to already fragile societies. Scientists increasingly view fire, ash, and dust not as isolated phenomena, but as interconnected elements of a system in upheaval. A spark, whether from a comet, volcanic activity, or natural climate stress, ignited fires. Those fires released soot and carbon into the atmosphere, amplifying cooling. Destroyed ecosystems produced more dust, which further altered climate patterns and hindered recovery. This feedback loop may help explain why the Younger Dryas persisted for more than 1,000 years. For people living through it, the burden was immense. They faced cold that shortened growing seasons, floods that reshaped rivers, and fires that consumed the land. Each challenge alone would have been severe. Together, they created a world in constant flux. Survival required flexibility, cooperation, and ingenuity, and archaeological evidence shows that humans responded with all three. In North America, the decline of the Clovis culture may reflect the combined impacts of fire, dust, and the loss of large animals central to their way of life. In the Near East, similar pressures may have pushed communities toward early farming as they sought stability. Across Africa and Asia, shifts in vegetation and rainfall forced new patterns of movement and adaptation. Everywhere, fire was woven into the broader narrative of the Younger Dryas. When scientists examine soot-darkened layers in Greenland's ice cores, or charcoal embedded in ancient soils, they are not just studying chemistry. They are glimpsing real events: skies black with smoke, forests reduced to ash, and people navigating landscapes transformed by flame. The Younger Dryas is often remembered as a time of ice, but it was equally an age of fire. Cold and flame coexisted, reshaping the planet in complex and interconnected ways. This paradoxal world, both freezing and burning, captures the true nature of the Younger Dryas. It was not a single catastrophe, but many overlapping crises, feeding into one another and leaving echoes that persist today. For those who survived, Earth was a place of sudden danger, where skies could darken without warning and entire worlds could vanish overnight. It felt as if the planet itself had come back to life. Change could be seen across every horizon, heard in newly growing forests, and felt by every human community living through it. For more than 1,000 years, Earth had remained locked in a cautious, restrained state. Ecosystems were limited, growth was slow, and abundance was rare. Then, in what amounts to an instant on geological timescales, life surged forward once more. The Holocene had begun, and the modern world started to emerge. This great renewal is recorded in the smallest traces of nature. Pollen grains preserved in ancient lake sediments tell a consistent story across Europe, the Middle East, and Asia. Open grasslands and low shrubs were gradually replaced by expanding forests. Once barren tundra transformed into dense woodland. In some regions, trees such as oak and hazel spread so quickly that landscapes changed within only a few human generations. Animals responded just as dramatically. Species adapted to cold conditions, like reindeer, withdrew toward northern regions. Meanwhile, forest animals such as deer and wild boar flourished in the expanding woodlands. Rivers and lakes also recovered, as rainfall patterns stabilized and glaciers retreated. Waterways regained strength. Seasonal flooding enriched floodplains with fertile soils, encouraging plant growth. Fish populations rebounded, wetlands expanded, and birds and small animals returned in large numbers. The natural world was not merely recovering, it was thriving with renewed energy unseen for millennia. For humans, this transformation brought opportunity. Communities that had struggled during the cold suddenly found themselves surrounded by reliable resources. In Europe, hunter-gatherers adapted to forested environments, developing new tools and strategies for hunting woodland animals, trapping birds, fishing rivers, and gathering nuts, berries, and fruits. Archaeological evidence shows a broader and more varied diet, reflecting the richness of the new ecosystems. In the Fertile Crescent, this environmental stability accelerated a major shift. Experiments with wild cereals, begun during the harsh, Younger Dryas, now flourished under warmer and more predictable conditions. Crops ripened consistently, villages expanded, and storage facilities grew. Early domesticated plants appeared, followed by animals such as goats and sheep. These developments created food systems that were more controlled and reliable, allowing settlements to become permanent. Over time, these settlements laid the foundations for the world's first cities. Population growth followed abundance. Communities grew larger and more complex. Archaeological burials from this era show early signs of social differentiation, with some individuals interred alongside richer grave goods. Trade networks expanded, carrying materials like obsidian and shells across vast distances. As nature stabilized, human societies entered a new phase of organization and ambition. Yet this renewal was not uniform everywhere. In some regions, warming led to drying rather than fertility. Parts of North Africa briefly turned green before becoming arid once again, forcing migrations. Elsewhere, rising seas swallowed ice age coastlines, erasing entire settlements. For many, the Earth's reawakening brought both prosperity and loss. What stands out is how quickly people adapted. Communities relocated in response to rising waters. Hunting methods shifted as forests spread. Droughts encouraged innovation rather than collapse. The hardships of the Younger Dryas had strengthened human resilience, and the Holocene allowed that resilience to evolve into creativity. Culturally, this renewal may have inspired powerful stories. After generations of cold and uncertainty, the return of warmth likely felt miraculous. Myths of rebirth, renewal, and lost golden ages may reflect real memories of watching the world come alive again. Just as flood and fire myths may echo earlier disasters, stories of paradise regained may preserve memories of this profound transformation. Geologically, the Earth was also adjusting. As massive ice sheets melted, land previously weighed down by kilometers of ice slowly rebounded. Coastlines shifted not only because of rising seas, but because the land itself was moving. Earthquakes and volcanic activity became more common in certain regions as the planet readjusted. For those alive at the time, the pace of change would have been impossible to ignore. A person born near the end of the Younger Dryas could, within their lifetime, witness forests filling valleys, rivers flowing where dry channels once lay, and animals returning in extraordinary numbers. The planet was not changing quietly, it was visibly transforming before human eyes. This period also triggered widespread migration. As climates improved, people moved into lands that had once been uninhabitable. Northern Europe and Siberia saw renewed settlement. Across the Americas, societies adapted to expanding forests and grasslands. In Australia, Aboriginal communities continued reshaping traditions in response to environmental shifts. The Earth's renewal was global, touching every continent. Looking back, the transition into the Holocene marks a turning point in human history. Agriculture took hold. Villages became towns, trade expanded, and social complexity deepened. The stable climate that followed allowed civilizations to rise. Without it, History as we know it might never have unfolded. The end of the Younger Dryas was sudden, but it opened a door. Humanity moved beyond mere survival and began to flourish. Abundance allowed innovation, planning, and permanence. The world changed, and humans changed with it. This story also carries lessons for today. The Younger Dryas reminds us that Earth's climate can shift rapidly and unpredictably. Stability is never guaranteed. But it also shows that humans are remarkably adaptable. Faced with cold, drought, fire, and scarcity, people did not disappear. They learned, cooperated, and innovated. Crises, this history shows, often spark transformation. Agriculture was born not from comfort, but from hardship. Scarcity forced experimentation, and experimentation reshaped the future. Climate change, then as now, was uneven, affecting regions differently and demanding local solutions. Perhaps the most important lesson is humility. The climate system has tipping points, and small disruptions can trigger massive change. Today, unlike the past, humans are influencing those systems directly. That gives us responsibility. We cannot stop natural forces, but we can decide how. We respond to warning signs. The Younger Dryas is not just ancient history. It is a message preserved in ice, soil, and stone. It reminds us that abrupt change is possible, that resilience matters, and that adaptation must come before catastrophe. Humanity once endured a world transformed. The question now is whether we will act wisely enough to face the changes ahead.